Welcome to the second part of 6.2, differential equations, Newton's law of cooling. So that's what we're going to focus on today. So the first thing we're going to do is we're going to go through the derivation of the formula for Newton's law of cooling. So the rate of change in temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium, meaning the room temperature. So if we kind of go through here, the rate of change, which is what we're calling y prime, is proportional, so we have that proportionality constant, to the difference between the object's temperature, so we're going to call that y, and the temperature of the surrounding medium, r, which we're going to call the room temperature. So another way we can write this, because it's talking about temperature in terms of time, so we could say, okay, dy dt equals k times y minus r, and now we're just going to solve this differential equation. All right, so multiply both sides by dt, divide by y minus r. We can do our u substitution when we're ready to integrate it, and what we will then get is we're going to get ln of the absolute value of y minus r equals kt plus c. So getting y, undoing this, we need to then rewrite it in exponential. So y minus r is equal to e to the kt plus c. But remember this e to the kt plus c, we could really rewrite that as e to the kt times e to the c, right? And this just turns into a constant anyways. So in the grand scheme of things, what we have is y is equal to c times e to the kt, and then we just have to add r to the other side. All right. We could go ahead and rewrite it as y equals c times b to the t plus r, where we are letting e to the k is what b is equal to. And that's kind of how we're going to do so in the next example that we go through. All right, so let's look at this example. Okay, so this example that we're dealing with today it's a little on the morbid side, but okay, we're going to go with it. So when a murder is committed, the body, originally at 98.6 degrees Fahrenheit, cools according to Newton's law of cooling. Suppose that after 2 hours, the temperature is 95 degrees Fahrenheit and that the temperature of the surrounding air is a constant 68 degrees Fahrenheit. So that's our room temperature there. Okay, so that's R. All right, room temperature. So what we need to do is we need to solve for our C and we need to get our K. So the first thing we're going to do is we're going to use the initial temperature of the body, right? The body originally at 98.6 degrees. So we're going to use that to find our C value. So we plug 0 in for T, we plug 98.6 in for Y, and R is 68. So as we go through and we solve, we get C to be 30.6. So we have our equation so far, Y equals 30.6 e to the kt plus 68. But now we need this k, or we could also solve for e to the k. So let's go through that next step. So now we have to use the fact that we found the body 2 hours later and the temperature was 95 degrees. Okay, so plug 95 in for y and 2 in for t. We're going to solve for k. So subtract 68, divide by 30.6. So e to the 2k is equal to 27 over 30.6. Getting k by itself, we're going to switch to ln, right? Take the natural log, and we've got ln of 27 over 30.6 divided by 2 is what our k value is. So what you can do on your calculator is right away do e to that k value. And we can store that answer as b. So what we're doing is we're storing e to the k. All right? So e to the k, and then we have our equation. So I'm calling e to the k, that whole thing, b. So then when we write our equation, we really have y is equal to 30.6 b to the t plus 68. And remember, b is equal to e to the k. So now, I want you to try graphing the temperature against time. Okay, sketch this graph really quickly, check back, see how you did. All right, so hopefully you have this asymptote at y equals 68 because that's our room temperature. Our body starts at 98.6 degrees, and then it'll eventually approach 68 degrees because that's our room temperature. So that kind of leads us into part C, what happens to the temperature in the long run. Show this on the graph and algebraically. Well, on the graph, we can see we've got this asymptote at y equals 68 degrees. So it's approaching 68 degrees. Algebraically, how do we show that? Well, we want to take the limit, right? The limit of our y as t goes to infinity. So when we do that, this b to the t goes to 0. So we end up with 68. So that's algebraically showing it. Now we're going to do one last step. Let's suppose you're doing a little bit of investigation yourself. So if the body is found at 4 p.m. at a temperature of 86 degrees, when was the murder committed? Let's see if you can figure this out on your own using your ordered pair, t, 86, and solving for t. Go ahead, give it a try, come back and check. So as you go through the process, y is 86, t is t, subtract 68, divide by 30.6, and now remember b is equal to e to the k, right? So as we're going through and we're solving for t, we've got ln of 18 over 30.6 divided by ln of b, so you take the natural log of both sides here, and you have that b stored, so you should have gotten t to be about 8.5 hours. So what time does that put the murder taking place? Well, if the body was found at 4 p.m., right, and we are going to subtract 8.5 hours, that would put us at 7:30 a.m. If you have questions, let me know.